Hello and welcome to our 12th lecture on our course on photonic devices. On today's lecture we're going to discuss heterojunctions and heterostructures. So as we've seen, heterojunctions are junctions between different semiconductor materials. So you have a p-n junction between material 1 and material 2, usually different alloys with different compositions and as well as band gaps. So this is used to refer to the junction itself. On the other hand, a heterostructure is a structure composed of one or more heterojunctions. So the device or the structure itself, which is made up of heterojunctions, is a heterostructure. So usually simple and double heterostructures are used to make sources as well as detectors. An important concept is the double heterostructure, so DHS. So the double heterostructure is composed of a semiconductor material sandwiched between layers of a different semiconductor material. So in our example here we have a middle gallium arsenide layer which is lightly p-doped, sandwiched between two aluminum gallium arsenide layers, which is a gallium arsenide alloy with aluminum in its composition, where on the left here you have a heavily p-doped aluminum gallium arsenide layer, and on the right you have a heavily n-doped aluminum gallium arsenide layer. So the N plus and P plus here are used to indicate heavier doping, and the P lighter doping, which means less dopants. But well, you have different materials here forming different junctions, and therefore this is an example of a double heterostructure. Since semiconductors with different band gaps are used, there are discontinuities in the band edges. So what this means is that if we look at the band diagram, for example, this semiconductor here might have a larger band gap, so this would be the conduction band and this would be the valence band, and this in the middle here the forbidden gap, whereas this semiconductor in the middle here might have a smaller band gap, and the semiconductor on the left is the same as the one on the right here, so it would have the same band gap. But as you can see, so conduction band and valence band here, as you can see, there are discontinuities in the conduction band edge as well as the valence band edge because of these different band gaps that these semiconductors present. So these discontinuities lead to the formation of potential barriers, which we can see, and potential wells. Such barriers are responsible for confining carriers, electrons and holes, charge carriers, to small regions in space. So for example, in the structure we've exemplified here, under certain conditions you might have a lot of carriers in this middle layer here, so a lot of electrons in the conduction band being in some way imprisoned or trapped in this region, and a lot of holes also in the valence band of the same region. Okay. So due to the confinement, the carrier concentration in these regions can become very large, and the importance of this is due to the fact that some gain characteristics of sources and other devices is dependent on the carrier concentration. So for light sources, for example, if you have in the same region lots of electrons and lots of holes which can recombine, the gain for light emission can be very, very large. So that's the importance of the double heterostructure. Before we start talking about double heterostructure, let's talk about a simple heterostructure with a heterojunction. So let's consider the heterostructure, simple heterostructure consisting of a heterojunction between a p-type aluminum gallium arsenide and an n-type gallium arsenide layer. Now, since these two, the aluminum gallium arsenide and the gallium arsenide, have different band gaps, there's a gap discontinuity in the junction, which we'll see in a moment. If the semiconductor is not in physical contact, so if it's not in physical contact, the Fermi level of the p-doped aluminum gallium arsenide is at a lower energy than that of the n-doped gallium arsenide layer. So this is illustrated right here. You have the p-doped aluminum gallium arsenide, since it's p-doped, the Fermi level is lower than halfway between the conduction and valence band, so it's a little lower towards the valence band. And here is the n-doped gallium arsenide, which is a smaller band gap semiconductor. It's n-doped, so the Fermi level is a little higher towards the conduction band, and we can see that because of the difference in the band gaps here, there are discontinuities at the conduction band edges and valence band edges across the junction, okay? And also the way that these energy bands are distributed in space, we can see that the Fermi level in the p-type aluminum gallium arsenide is lower than the Fermi level in the n-type gallium arsenide layer. Okay, so this Fermi level is a little lower than this one right here. Now, when the junction is brought to physical contact, when it's brought together, there's a difference in carrier concentration on either side of the junction. This material is a p-type material, so it has lots of holes. The hole concentration is very large, the Fermi level is lower. This material is an n-type material, so the electron concentration is larger, the Fermi level is closer to the conduction band, so it has lots of electrons. So naturally, electrons will tend to diffuse to the p-type material, and holes from the p-type materials, which are the majority carriers here, will tend to diffuse to the n-type material. So these carriers do need to cross a little bit of a barrier here, so the electrons need to gain a little bit of energy, but this energy is not too large compared to the band gap itself, and some electrons will have enough energy to overcome these barriers, and the same thing will happen for holes here. So you will have a diffusion of electrons in the conduction band into the p-type material, and holes into the n-type material, as illustrated here. And just as in a regular p-n junction, these carriers will recombine close to the junction, forming a depletion layer close to the junction here, where you will have, on the p-type material side, negative ions here, which are unpaired with respect to holes, and on the n-type material side here, you have positive immobile ions close to in the junction region. So the majority carriers inside the gallium arsenide layers are electrons with a carrier concentration which we can consider to be N, and the majority carriers inside the aluminum gallium arsenide, which is a p-type material, are holes with a carrier concentration P. So we're saying that in the p-type material we have a P holes per centimeter cubed, and in the n-type material we have N electrons per centimeter cubed in the conduction band. The holes are in the valence band, and as we've said, they will diffuse. So since there are more electrons in the n-type gallium arsenide material, there's a flow of electrons towards the left, towards the p-type material. So the electrons will flow, as we've said here. And since there are more holes in the p aluminum gallium arsenide material, p-type aluminum gallium arsenide material, there's a flow of these carriers towards the right, towards the n-type material. Okay. So more holes here, Fermi level is lower, not so many holes here, they will flow to the right. So this will constitute currents, right, diffusion currents, just like in a regular p-n junction, and these currents lead to positive immobile ions in the n-type gallium arsenide material side of the junction, and negative immobile ions in the p-type aluminum gallium arsenide side of the junction. So these immobile ions are illustrated here. Don't worry about the band diagram for now, but this happened because, again, the holes which are in excess in this material diffused and recombined with the electrons which were pairing up with the positive immobile ions. So these immobile ions were left unpaired, and therefore you have a net positive charge here consisting of the lattice immobile ions. The same thing happens when the electrons, which are the majority carriers here, diffused into the p-type material across the junction and recombined with the holes here, and by doing so they left negative immobile ions which are unpaired, and so you have a net spatial charge here, a negative charge distribution in space, which for a certain width corresponding to the depletion region you have these net charges. Positive charges inside the N-type gallium arsenide material translate into a positive electrostatic potential of this side with respect to the P-type material side. And also, in the same manner, the negative charges, the negative immobile ions inside the P-type material translate into a negative electrostatic potential. So what we're saying here is that, just like in the parallel plate capacitor analogy, this would be the positive plate, and it would be at a higher V, a higher electrostatic potential. This would be the negative plate, which would be at a lower electrostatic potential. So this is what happened. These regions are neutral, so the potential here will be the same across this region, right? So you have a positive potential and a negative potential on this side and this side respectively, and there will be a potential drop across the junction, electrostatic potential drop. But we have to remember what we've seen before with respect to the relationship between potential energy and electrostatic potential. So the electrostatic potential V is defined as a potential energy per unit test charge. So this what we're saying here is that V is equal to potential energy, potential energy per unit test charge. Therefore the potential energy is V times Q. And when we're talking about the band diagrams, these are the band diagrams for electrons. So the charge here is the electron. Therefore we need to substitute the electron, which has a negative charge with absolute value equal to the elementary charge here. And this shows us that if we want to obtain the potential energy from the electrostatic potential, we need to multiply it by minus E, or minus a constant. Okay, and this means that the electrons in the N-type gallium arsenide material side have an overall lower potential energy because they have a larger electrostatic potential than the ones in the P-type material. So this is exactly what happened in the regular PN junction, right? The line of thought is the following. As we've said, this side is at a higher electrostatic potential than this side, but since we need to, in order to obtain the potential energy or the energy, we multiply V by minus the elementary charge. This means that this side is actually at because of these charges, at a lower potential energy, right? So the whole band diagram will need to go down, as the depletion region formed because of this drop in potential here, which will turn to be a drop in potential energy from left to right, because of what we just said. And the bands will bend in the same way as they did, for a regular PN junction. So when we're talking about a homostructure rather than a heterostructure, in that case, if you had a similar situation, the Fermi levels would be aligned, and you had the P-type material here and the N-type material here, and the bands would bend just like this, in this S shape. But so this would be the P-type and this would be the N-type side, but there were no discontinuities. Okay, here exactly halfway, or around halfway, inside the junction, inside the depletion region, you have these discontinuities, which originally we had when the materials were not in contact as well. These are these discontinuities right here. They are still there, and so when the bands bend, the band bending will have the same parabolic shape up to the discontinuity, then this discontinuity will still be there, and you'll have the other side of the parabola here, right, in the n-type material. So it's exactly the same thing here, except for the discontinuity, which needs to be taken into account right at the junction itself. So the bands will bend in the junction region in a similar way to a regular homojunction we've just illustrated here, but you have the discontinuities which need to be taken into account. So the discontinuities delta EC and delta EV, right, the discontinuity in the conduction band edge and the valence band edge remain after physical contact. And notice that these discontinuities are halfway between materials inside the depletion region. So these discontinuities are exactly at the center of the junction where the p-type material meets the n-type material, right in the middle here. Also, the discontinuity delta EC implies an additional energy barrier that electrons have to overcome in order to flow to the p-type material. So again, once the bands bend and the Fermi level align, now the electrons which are here in the conduction band, majority carriers in the n-type material, need to overcome a much larger, because of the bending of the bands, a much larger barrier here in order to diffuse to the p-type material, right? This barrier corresponds to the electrostatic field, so the E field, right, which we discussed in our previous lecture, the electrostatic field, which prevents the electrons from going that way, right? Negative charges tend to move in the opposite direction of the electric field. So this field is related to this barrier right here. So the electrons, once the junction is brought into contact, the electrons will have a difficult time overcoming this barrier, so very few electrons will be able to do so, and the drift current, along the direction of the electric field will exactly cancel out the diffusion current, and things will be in equilibrium. Now they can be taken out of equilibrium if you apply a direct or reverse polarization voltage here, right? And then these will mean that the bands will bend again. For example, the n-type material band diagram, the whole band diagram might move down or up depending on the potential that you apply across the junction, the external potential, okay? But notice that now we have potential barriers which are not of much use in a simple heterojunction, but in the case of the double heterostructure, which we'll see in the second part of this lecture, it's much useful in order to confine carriers to a small physical region, making excellent light source devices.